Ever feel like you're just drowning in information sometimes? Whether you're prepping for something big at work, trying to learn a new skill, or maybe just curious about a topic.
Oh, absolutely. The sheer amount of stuff out there can be overwhelming.
Right. What you really want is like a clear path, a shortcut to actually getting it without getting bogged down in all the details.
Exactly. You want the core insights.
And that's precisely what we aim to do here. Welcome to the deep dive.
Glad to be diving in.
Today, we're really digging into operational excellence, and we're looking at it specifically through the lens of Six Sigma Green Belt training.
A really powerful lens.
Our mission basically is to cut through all that complexity. We want to pull out the most vital nuggets of knowledge, maybe some surprising facts too, all to help you get up to speed fast on this methodology.
And we're drawing heavily from Vishnu Rayapati's material as our guide for this exploration. It's great stuff.
It really is. So let's start with the big picture. Six Sigma.
Mhm.
It's more than just tools, isn't it?
Oh, much more. Think of it as a philosophy, really. And yes, a very comprehensive toolkit, but it's all geared towards this relentless pursuit of, well, near perfection.
Near perfection meaning.
The ultimate goal is pretty mind-blowing.
Yeah.
Reducing defects down to just 3.4 per million opportunities.
Wow. 3.4 in a million. Just pause on that.
Yeah, think about what that means. If you're running a hospital, that's aiming for only 3 or 4 errors in a million procedures. For an airline, virtually flawless flights.
Okay, that puts it in perspective.
It's not just about, saving a bit of money here and there. It's about hitting a level of quality and consistency that fundamentally changes things: safety, customer trust, how efficiently you operate.
Yeah.
The real insight isn't just that number, 3.4, it's the mindset shift needed to even chase that level of performance.
That's incredible. And this whole quest for quality, it's not new, right? This has been around forever.
Absolutely. It's a timeless pursuit.
There's that great quote by William A. Foster: "Quality is never an accident. It is always the result of high intention, sincere effort, intelligent direction, and skillful execution." It goes on, but the point is, it takes deliberate effort.
Exactly. And it makes total sense that improving quality is probably the single biggest lever you can pull to boost profits, make customers happier, and frankly, beat the competition.
So who were the key figures who really shaped this thinking, the pioneers?
Yeah, there were several giants, really. Maestros, you could call them. Their ideas laid the groundwork.
Like W. Edwards Deming. He was huge in Japan's manufacturing boom after the war, wasn't he?
Absolutely instrumental.
Yeah.
Deming hammered home the importance of understanding variation.
Yeah.
He introduced statistical process control, or SPC.
That's about telling the difference between unusual problems and everyday fluctuations.
Precisely. He talked about special cause variation, think a machine suddenly breaking down, totally unexpected versus common cause variation, which is just the inherent normal ups and downs in any system, like traffic varying slightly day to day.
And you deal with them differently.
Totally. You jump on eliminating those special causes right away. But for common causes, you need to improve the whole system, bit by bit. He also gave us the Plan-Do-Check-Act cycle, the PDCA model. Still fundamental for continuous improvement. His book, Out of the Crisis, classic stuff.
Okay. And then Joseph Juran.
Juran, yeah. Came over from Romania. His big thing, which most people have heard of, is the Pareto principle.
The 80-20 rule.
Right. 80% of your problems usually come from 20% of the causes. But Juran's genius wasn't just stating the rule. It was the discipline he advocated for actually finding that vital few 20%.
Because it's easy to get distracted by the easy-to-spot stuff.
Exactly. Companies waste tons of effort on the trivial many. Six Sigma, building on Juran, forces you to use data to pinpoint that critical 20% that gives you 80% of the improvement. It often surprises you where the real leverage is. He also developed the quality trilogy: planning, improvement, and control.
Got it. And Philip Crosby, he had a pretty straightforward take, didn't he?
Very straightforward. Quality, for Crosby, was simply conformance to requirements. That's it.
No fuzzy stuff about delighting the customer?
Nope. Just did it meet the spec? Yes or no? His big impactful idea was 0 defects. Anything less than perfect conformance was unacceptable. Quality was measured by the cost of not conforming. Simple, powerful.
And Kaoru Ishikawa,
Yeah.
from Japan, pioneer of quality circles.
Ishikawa's major contribution we still use all the time is the cause and effect diagram.
The fishbone diagram.
That's the one, or Ishikawa diagram. It's a brilliant visual tool for systematically listing out all the possible causes of a problem. It forces teams to dig deep, look beyond the obvious symptom.
Really helps structure that brainstorming.
Definitely. The level of detail in a good fishbone diagram often shows you how well the team truly understands the issue.
Okay, one more, Junichi Taguchi.
Taguchi, another Japanese innovator, he focused on improving quality while also cutting costs, which was crucial post-WWII.
Yeah.
His concept of robustness is fantastic.
Robustness, meaning
Designing products or processes so they work well, despite things you can't control, what he called noise. Think designing a phone that works reliably, whether it's freezing cold or boiling hot outside, or a baking recipe that turns out okay, even if your oven temperature fluctuates a bit.
so making things resilient to real-world messiness.
Exactly. He also gave us the quality loss function, which quantifies how value drops off, even if something is technically within spec, but not perfectly on target.
Interesting. So all these gurus laid the foundation.
Right. And what's cool about Six Sigma is that it didn't just appear out of nowhere. It consciously built on these foundational ideas, integrated the best bits, and then formalized them into a more data-heavy structured system.
And the roots go way back. You mentioned gas.
Yeah, incredibly, the statistical basis, the normal distribution curve, goes back to Johann Carl Friedrich Gauss in the early 1800s.
Wow. But the name Six Sigma came much later.
Much later. Coined by a Motorola engineer, Bill Cohen. But the real standardization came in 1986 from Bill Smith, also at Motorola.
What did he standardize?
He standardized how defects were measured. This is the key leap. It allowed measurement in terms of millions of opportunities, not just thousands. Suddenly, you had much finer visibility into quality issues.
And the results.
Huge! Motorola itself documented something like $16 billion in savings from their Six Sigma efforts. That got other companies' attention fast. Big names like GE, Citibank jumped on board. Its power to deliver quantifiable results became undeniable.
Okay, so that history makes sense. But you hear about lots of quality initiatives, TQM, Lean, etc. What really makes Six Sigma different? What are its unique superpowers?
That's a great question, because it does have some distinct features that often make it more effective. Some real aha moments in how it operates.
Okay, like what?
Well, first, it's incredibly comprehensive. It's not just one technique that pulls together best practices from lots of other quality approaches and integrates them into that full DMAIC lifecycle. Define, measure, analyze, improve, control.
Right, the DMAIC framework.
And it provides specific tools for each of those phases. Plus, it's super adaptable. You can apply it in manufacturing, sure, but also finance, healthcare, IT, service industries, small companies, big corporations. It gives you this unified roadmap.
Okay, comprehensive. What else?
Second, it has a strong project-based approach. This is quite different from some older quality methods that were more ongoing.
How so?
Six Sigma efforts are treated like distinct projects. They have defined start and end dates, a formal project charter outlining the goals, specific deliverables. It uses standard project management tools, Gantt charts, PEERT charts, you name it. It takes fuzzy improvement ideas and turns them into manageable, trackable projects.
So it brings that project management discipline.
Exactly. Third, it fosters a very cohesive process-based approach. From the get-go, you're creating detailed process maps.
Why is that so important?
Because it gives everyone a shared, holistic view of how work actually flows across the organization. You see the handoffs, the dependencies. It makes it much easier to spot where the bottlenecks or problem areas really are. You see the whole system, not just isolated parts. Think about mapping out every step in, say, processing an insurance claim. You quickly see where delays happen.
Right, it connects the dots.
Definitely. Fourth, and this is a big one, is its quantitative approach. This is where the rigor really comes in.
More than just counting defects.
Much more. A lot of older quality efforts, frankly, struggle to rigorously measure costs and benefits. Six Sigma insists on using robust statistical methods. Goals have to be measurable, quantifiable, and directly tied back to the organization's strategic objectives.
So it proves its own value.
Precisely. It helps you select the projects that will give you the biggest bang for your buck, the maximum benefit for the least cost. It speaks the language of business results measured in dollars, time saved, defects reduced.
Okay, that makes sense. Anything else?
Yes, one more key piece. Commitment from all levels. Six Sigma isn't just pushed down from the top or bubbling up from the bottom. It formalizes an organizational structure for these projects.
Like the different belts.
Exactly. You've got your deployment champions, usually senior leaders, providing the crucial sponsorship and resources. Master black belts and black belts are the deep experts, the coaches. Green belts often lead smaller projects or support black belts. They're the operational liaisons. Then you have the project teams doing the work and subject matter experts lending specialized knowledge.
So everyone has a defined role.
Right. And this creates this powerful sense of shared ownership and responsibility. It's not just someone else's job to improve things. It builds buy-in across the board.
Okay, so comprehensive, project-based, process-focused, quantitative, and commitment-driven. That paints a clear picture of what sets it apart.
Those are really the core differentiators.
All right, so let's get into the nuts and bolts then. The DMAAC framework, you mentioned it's the tactical roadmap. Let's walk through it, starting with the first couple of phases. Define and measure.
Sounds good. So, define. Phase 1. The objective here is pretty straightforward. You need to understand why you're doing this project, what's its purpose. You need to establish how you'll measure success, the metrics, and you need to state the problem clearly.
So getting everyone on the same page about what you're trying to fix and why.
Exactly. The key inputs you need are, first, the actual need for the project. Is it about boosting customer satisfaction, cutting costs, reducing errors, gaining a competitive edge? What's the business driver?
And you mentioned sponsorship.
Crucial. You need that executive management sponsorship. They provide the high-level mandate, the resources, the backing, and you need a dedicated core team, a project manager, maybe a Six Sigma expert like a green or black belt, and other key people with the authority to make things happen.
What tools do you use and define?
Well, understanding the organization hierarchy is surprisingly important, knowing who to talk to, who controls resources. The high-level process maps are essential early on. Just a simple flow chart showing the main steps of the process you're looking at.
Helps visualize the flow.
Right. Clarifies the steps, shows alternatives, gets the team aligned. Another powerhouse tool here is the Pareto chart.
Back to the 80-20 rule.
Exactly. This is where you apply it. Let's say an airline is looking at lost baggage complaints. A Pareto chart might quickly show that, say, 50% of lost bags are due to wrong tagging, and another 30% are human error during transfer. Boom. You know immediately where to focus your limited resources for the biggest impact, the vital few causes.
Makes sense. Focus on the big hitters first.
Then you've got a range of idea generation and categorization tools. You might use simple surveys or focus groups to get customer input directly. The Kano model is neat. It helps you understand different types of customer requirements, basic needs, performance needs, and those attractive delighters.
Okay.
Use brainstorming, of course, maybe the nominal group technique, NGT, which is a more structured way to brainstorm and prioritize issues, helping to reduce the influence of dominant personalities. Multi-voting helps narrow down lists. Affinity diagrams help group similar ideas together. Lots of tools to get solid input.
So what comes out of the define phase? What are the deliverables?
Key outputs. First, the project charter. This is the formal document. It authorizes the project, outlines the objectives, scope, boundaries, lists resources, timelines, how you'll know when it's done. It's the project's birth certificate.
Okay, the official mandate.
Then, established metrics. You need quantifiable ways to measure success. Primary metrics, like the defect rate or cycle time, and maybe consequential metrics, things you want to make sure don't get worse while you fix the main problem.
Like, don't reduce call time if it tanks customer satisfaction.
Exactly. You also need a clear problem statement. This compares the current as-is performance baseline with the desired to be improvement goal. Very specific. And finally, define roles and responsibilities for everyone on the team.
Got it. Define sets the stage. What about phase 2? Measure.
Measure is all about data, data, data. The objective here is to collect the data you need to really understand the current process. You also need to validate your measurement systems. Make sure the data you're collecting is actually accurate and determine your starting point, your baseline process capability.
Quantifying reality.
Precisely. And a couple of crucial concepts here. First, understanding data types. It really matters if your data is great. Discrete things you count, like the number of errors, number of calls, or continuous things you measure on a scale, like time, weight, temperature, money.
Why does that distinction matter so much?
Because it dictates the statistical tools you can use later on. Different tools work with different data types. Sometimes you might convert continuous data, like temperature, into discrete categories like too cold, just right, too hot, for certain analyses.
Okay. Data types. What else?
Measurement scales, how you classify your data. There's nominal, just categories with no order, like types of defects. Ordinal, where categories have an order, like satisfaction ratings, poor, fair, good, excellent. Interval, where the distance between points is equal, but there's no true zero, like Celsius temperature. And ratio, which is a meaningful zero, allowing true ratios, things like cost, time, height.
Again, helps choose the right analysis tools later.
Exactly. Get the data type and scale wrong, and your analysis could be flawed.
Okay, so what tools do we use in Measure?
Simple but effective. Check sheets. Just well-designed forms to make collecting data consistent and easy. Like that airline example. A check sheet at baggage handling might have columns for different error types, and staff just make a tick mark each time one occurs. Simple, but gets you raw data.
Okay, straightforward.
Now this one is really interesting and super important. The Gauge R&R study.
Gauge R&R, what's that about?
It stands for Gauge Repeatability and Reproducibility. It's a powerful study to figure out if your measurement system itself is reliable. Is the variation you're seeing real, or is it just noise from your measurement process?
How does it work?
It looks at two things. Repeatability. If the same person measures the same thing multiple times with the same tool, how consistent are the readings? Reproducibility. If different people measure the same thing with the same tool, how consistent are the readings?
So it checks both the tool and the people using it.
Exactly. Imagine umpires rating baseball pitches as valid or invalid. A Gauge R&R study could involve 3 umpires rating the same set of pitches twice. You analyze the data to see how consistent each individual umpire is, repeatability, and how much agreement there is between the umpires, reproducibility. If the overall accuracy is low, say only 32% agreement in the example, it tells you your measurement system. Maybe the umpire's training or criteria is flawed. You can't trust the data until you fix the measurement system itself.
Wow, okay. That's critical. If your measurements are off, everything else is built on shaky ground.
Absolutely. Another useful tool is the run chart. Simple plots of data over time. Great for spotting trends or patterns visually, especially early on with continuous data.
Like tracking call handle times.
Perfect example. You plot each call's duration. You can quickly see outliers. Maybe one call took 20 minutes, a special cause worth investigating. Or you might see a trend, like 7 consecutive calls taking longer than the average median, suggesting maybe the process itself has shifted. Helps you target where to look next.
Okay. Visualizing the data over time.
You'd also revisit and refine the detailed process maps and Pareto charts you started in, define, adding more detail now that you have more data. And you continue using those stakeholder tools, Kano model, quality function deployment, QFD, to ensure you're measuring things that actually matter to the customer.
Right, keeping the customer focused. So outputs from Measure.
You come out with well-defined processes, now backed by data. A clear understanding of your baseline process capabilities. How well is the process actually performing right now? You identify the key process parameters affecting critical to quality, CTQ, factors those things that must be right for the customer, like latte temperature being just right.
And the cost.
Yes, you'll have quantified the cost of poor quality, COPQ, breaking it down into appraisal costs, inspections, internal failure costs, rework, scrap, prevention costs, training, and external failure costs, warranty claims, lost customers, highlighting hard savings, soft savings, cost avoidance, and crucially, you have validated measurement systems. You know you can trust your data going forward.
Okay, that's huge. Define the problem, measure the reality, and now we get into the detective work, right? Analyze.
Exactly. Phase 3, analyze. Now you dig deep into the data you collected. The objective is to analyze the current system, to pinpoint the root causes of the problems, identify failure points, major milestones, and risks. This is where you connect the symptoms to the actual disease.
What are the go-to diagnostic tools here?
The Ishikawa diagram, or fishbone, is still a workhorse. You gather a cross-functional team and brainstorm all the potential causes for the problem you defined, organizing them under standard categories like manpower, methods, machines, materials, measurement, environment.
We talked about that for the coffee shop example, inconsistent lattes.
Right. The detail level on that fishbone really shows how deeply the team understands the potential contributing factors. It guides further investigation.
Okay. What else?
Failure mode and effects analysis, FMEA, is another really powerful systematic tool. We touched on it, but here you really apply it. You identify potential ways a product or process could fail, failure modes, what the consequences would be, effects, and what the potential causes are.
And then you rate them.
Yes. For each failure mode, you rate the severity of its effect. 110, how bad is it for the customer? The likelihood of occurrence, 110, how often does it happen? And the likelihood of detection, 110, how easily can we catch it before it reaches the customer?
And multiply them together.
Right. Severity X, occurrence X detection gives you the risk priority number, RPN. A high RPN flags the biggest risks you need to address first. Remember that ear thermometer example. If thermometer not working properly, leading to a wrong temperature registered, has high severity, occurs sometimes and is hard to detect, its RPN might be, say, 288. That screams, fix this now.
Okay, FMEA helps prioritize the risks.
Definitely. You also might use hypothesis testing, statistically speaking. This is where you use sample data to make inferences about the whole population. Are the average call times from two different call centers truly different, or is the difference just due to random chance? Hypothesis testing helps you make that call statistically, quantifying the risks of being wrong, type I error, seeing a difference that isn't real, or type 2 error, missing a real difference.
Getting into heavier stats there.
A bit, yeah.
Yeah.
But crucial for data-driven decisions. And finally, the process capability study. Now that you have data, you can calculate how capable your process actually is of meeting the customer specifications or requirements.
Like the latte temperature example.
Exactly. Or imagine a factory making spherical ball bearings. They measure the diameter of a sample. The capability study calculates metrics like defects per million opportunities, DPMO. Maybe they find their DPMO is 9180. That translates to roughly a 4 sigma process level. The goal is always to improve capability, which means decreasing the variation, making the process more consistent, and centered on the target. Less spread means fewer defects.
So Analyze tells you why the problem is happening and how bad it is.
Precisely. The outputs are critical.
Yeah.
You've identified the important causes of defects. You've distinguished between those pesky special causes of variation, which you want to eliminate, and the inherent common causes, which you need to reduce.
Right.
And you have your current DPMO and sigma level, that quantified baseline. Now you know exactly what you're up against.
Okay, the picture's clear. Time to fix it. Phase 4, improve.
Yes. The improve phase is where you design the solution. The objective is to identify, evaluate, and select the best solutions to fix the root causes you've found and analyze. You want to maximize the return on investment, ROI, and create a detailed plan for implementation.
So focusing on solutions, what tools help here?
Well, return on investment, ROI itself, is a key tool or metric. Project benefits divided by project costs. You constantly evaluate proposed solutions through this lens. Does the expected improvement justify the cost and effort?
Gotta make good business sense.
Absolutely. To compare different potential solutions, you might use a solution design matrix.
How does that work?
You list your potential solutions down one side, and your key decision criteria across the top, things like cost, time to implement, impact on defects, ease of use, etc.
Yeah.
You might weight the criteria based on importance. Then you score each solution against each criterion. The matrix helps you objectively compare the options and choose the one with the best overall weighted score. Like that popcorn manufacturer example, weighing cooking time, taste, cost, complexity to pick the best improvement project.
A structured way to choose the best path.
Exactly. Now, for more complex problems, design of experiments, DOE, is incredibly powerful.
That's complex itself.
It can be, but the concept is smart. Think of your process as a black box with knobs you can turn, inputs or factors, and a result you measure, output. DOE is a structured way to efficiently change multiple input factors at the same time, like changing grind size and water temperature for coffee, and see how those changes affect the output, taste, extraction time.
Instead of changing just one thing at a time.
Right, which is slow and often misses interactions between factors. DOE helps you find the optimal settings for all your key inputs much faster and more reliably. The benefits can be huge: better quality, faster cycle times, fewer defects, higher ROI. It helps you find that sweet spot.
Okay, DOE for optimizing the process settings.
And Taguchi's robustness concepts come back in here too. When designing the solution, you want to make it robust, less sensitive to those uncontrollable noise factors we talked about earlier.
Building resilience into the fix.
Precisely. And sometimes response surface methodology, RSM, is used, often in conjunction with DOE. It's another statistical tool to help visualize how different input combinations affect the output, often shown as contour plots or 3D surfaces, helping you pinpoint the absolute peak performance area.
So lots of powerful tools to design the right fix.
Definitely. The outputs from Improve are clear: cost-benefit analyses for the viable solutions, the final selection of the optimal solutions you're going to implement, and a detailed implementation plan outlining who does what by when. You're ready to make the change.
All right, problem analyzed, solution designed. Now, the final phase, control, making sure the fix actually sticks, right?
Exactly. Phase 5, control. The objective here is crucial. Ensure that the gains you achieved in the improve phase are sustained over the long term. You also need to control the ongoing project parameters, risk, cost, quality. You don't want things slipping back to the old ways.
How do you do that? What are the tools for sustaining improvement?
A cornerstone is the control plan. This is a living document that details exactly how you'll monitor the improved process going forward, what gets measured, how often, by whom, what tools are used, and critically, what actions should be taken if the process starts to drift out of spec. It's the playbook for maintaining control.
Proactive monitoring.
Yes. And a key tool for that monitoring is statistical process control, SPC, specifically using control charts. We mentioned run charts earlier. Control charts are similar but more statistically robust. They plot process data over time, but they also include calculated upper control limits, UCL, and lower control limits, LCL.
Based on the process's natural variation.
Exactly. Data points falling within the control limits generally indicate the process is stable, exhibiting only common cause variation. But a point outside the limits signals a potential special cause. Something unusual has happened, the process is out of control, and you need to investigate immediately.
So it acts like an early warning system.
Precisely. And there's that handy rule of 7, often used with control charts. If you see 7 consecutive data points all above or all below the center line, the average, even if they're within the control limits, it's a strong indicator that the process mean has actually shifted. Time to look into why.
Okay, SBC keeps an eye on things statistically. What about broader methodologies?
Lean enterprise principles are often heavily integrated here. Lean is all about maximizing value by eliminating waste and accelerating flow or velocity. It's guided by Little's Law, which connects lead time, work in process, and completion rate. Basically, reduce the stuff clogging up the system and things move faster.
And Lean has its own set of tools.
Oh yeah, a fantastic toolkit. You've got 5S, sort, straighten, shine, standardize, sustain. It's a systematic way to organize the workplace for efficiency and safety. Get rid of clutter, have a place for everything.
Makes sense.
Then there's Kaizen, the philosophy of continuous improvement through small incremental changes made by everyone, every day. It fosters a culture where improvement is constant, not just a one-off project.
Empowering the front line.
Absolutely. Kanban is another key lean tool. It's a signaling system, often using cards or visual cues, to manage work in progress and inventory. It enables pull systems and just-in-time JIT production, reducing wasteful inventory buildup.
Like the coffee shop restocking beans only when needed?
Perfect example. And total productive maintenance, TPM, focuses on equipment. It's a holistic approach where everyone gets involved in maintaining equipment to maximize its effectiveness and prevent breakdowns. It targets the 6 big losses, like downtime, defects, reduced speed, etc., often measured by overall equipment effectiveness, or OEE. Keep the machines running smoothly.
So lots of ways to lock in the gains and keep improving.
One last crucial step in control: measurement system reanalysis. Periodically, you need to go back and revalidate your measurement systems using tools like Gauge R&R. Just because it was good 6 months ago doesn't mean it still is. Thermometers drift, people forget training. You need to ensure your ongoing measurements remain trustworthy.
Closing the loop on measurement integrity.
Exactly. So the outputs of control are really satisfying. You have implemented solutions that are verified and working. You have a potentially revised measurement system. You have that all-important control plan for sustaining the benefits. You have improved process capability. Your DPMO is lower. Your sigma level is higher. And vitally, you have documented lessons learned. What worked well, what didn't. Sharing these insights across the organization is key for future success.
Wow, okay, that's a comprehensive journey through DMAC. Define, measure, analyze, improve control. From understanding the problem to locking in the solution.
It really is a powerful, structured path.
So, reflecting on everything we've covered, from those foundational quality gurus to what makes Six Sigma unique, and now this deep dive into the DMAIC toolkit.
Yeah, it really underscores that Six Sigma isn't just about crunching numbers, is it? It's a whole business philosophy.
A philosophy aimed at perfection.
Or at least the relentless pursuit of it. It drives that data-driven approach to innovation, problem-solving, and ultimately delivering a much better experience for the customer, which in turn strengthens the business itself. It's about embedding that culture of continuous improvement.
Makes sense. It's a mindset shift supported by powerful tools.
Well put.
So for everyone listening, here's something to mull over. Knowing the power of this kind of quantitative analysis, this structured approach to continuous improvement, what's one or two of those vital few problems in your own work or even your life that you could start tackling? Maybe not full Six Sigma, but using that structured, data-driven mindset, aiming for your own version of zero defects. What could that look like for you?